everyone. So today we are going to talk about why cells divide. So far, this has kind of been hinted at, and we've seen how cells divide, but today we're finally going to see why they divide. What is the purpose of cell division? So one is growth, one reason is reproduction, and one reason is repair. Kind of a silly way to remember this is GRR, right? GR, just a silly mnemonic device, I guess. But cells need to divide in order for the organism to grow, to reproduce, and to repair damaged tissue. So we're going to look at some examples of each of these. So the first example is of growth. These are actually roots of, I think it's an onion plant. So these are the roots that, grow out of a seed and grow into the soil. They don't just grow magically, right? There are cells in the roots that reproduce to make new cells. That's how the root grows. So this is a time lapse of roots growing. And it's not growing in soil, it's growing in kind of like a gelatin substance so that you can see it. But at the tip here, there are cell division is occurring to elongate the roots. I don't know if you remember this, but when we did our microscope lab, the one with the cheek cells and the pond water and the allodia and all that, you actually looked at onion root tip cells to see cells dividing. This is what Rudolf Virchow looked at, that cells come from pre-existing cells. So right there, if you looked at this closer up in a microscope, you would see cells undergoing cell division, and you can actually stain the cells to see the chromosomes to determine what stage of mitosis they're in. Also, just another random fun fact, the movie Twilight, Edward Cullen, the vampires, there's a scene in the first movie, where they are looking at onion root tip cells under a microscope, and they're like pushing it back and forth, and you can actually hear them say like prophase, anaphase, metaphase. But I guess if you're in quarantine, you can go check it out, see what I'm talking about. But anyway, so that was growth. This is going to be repair. So planaria are a single-celled protist. They're actually quite large. You can see them with the naked eye. Under the microscope, you can actually see, their anatomy. We were supposed to do a lab with planaria. We were actually going to do this activity where you cut the planaria in half. They don't die. They are actually able to regenerate their limbs. So after a couple days, you can check in on them and you'll see their body parts start to grow back. So if you cut it in half, then each half will grow the missing half so that they become whole planaria again. And again, this is not, a magical process. In order to create the entire second half of the organism, the cells remaining after you chop it in half have to go through cell division. They have to make new cells. So that's what this process is. So I figured if we can't do the lab, we can at least watch a video. So this is the amputation. You actually take kind of like a scalpel and you can cut it in half. You can either do it laterally or like a cross section like this. So you can see this side, the two eyes are there, and then this is the tail. Okay, so this is the front half of the organism with the two eyes, and that's the tail. So then they're going to show you that the tail cells undergo cell division to regrow the head. So I'll just let this play. to skip ahead a little bit. So this is 5 days. You can see that the eyes have grown back, the head's back, and so only 5 days later, the cells that were in the tail are able to regrow the head. Okay? So that's regeneration. Other organisms can do this as well, higher order organisms like lizards, geckos, sea stars, right? I think it's the first Spider-Man movie with Andrew Garfield, where the scientist, loses an arm and tries to become a lizard to regenerate it. Right? There's all of these Hollywood examples of cell division, I guess. It seems magical, right, that it's able to regrow a limb. Mammals are not able to do this, but lower order organisms that aren't as complex can use instructions from the cells left in the tail to regrow the head, and it's all through cell division. And then the last is reproduction. So again, higher order multicellular organisms don't really use mitosis for reproduction. We can't make an entire new organism growing from our arm using cell division, right? But these are yeast cells and they reproduce through budding. You can actually see, like, here's a yeast cell and here's the bud coming off of it. So they are able to do this again through mitosis. When mitosis is used for reproduction like this, where one cell becomes two, and this is, the asexual reproduction of the organism, it's often called binary fission. It's the same process, essentially, right? The nucleus has to divide. You got to get the DNA split up into both cells. So it's still mitosis, but it gets a special name. It's called binary fission. And again, these are yeast cells. Yeast are a type of fungus. Okay, so you get the idea. Again, all of that is cell division. All of it's mitosis. Growth, repair, reproduction. Humans do it all the way down to, the simple yeast cells. So how do cells know when to divide, right? They know, okay, this organism has to grow. I need to make new cells. But, what actually forces a cell to divide? I'm just going to show you this real quick. So cells divide in order to stay small. That's the simple answer. There's this really cool interactive scale of the universe where you can see just how small a cell is. So I'm going to zoom in, all the way in. Okay, I went too far. Now this is like nanoparticles, like quantum physics. I'm a little too far. Okay, here we go. Proton, neutron. So subatomic particles. Then we get to an electron. Gamma ray wavelength. Right, this is the shortest wavelength, the highest frequency in the electromagnetic spectrum. Now we're at single atoms. Okay. Smallest thing visible to an electron microscope. These are really, really powerful microscopes. Again, still at single atoms. Now we're at a water molecule, a glucose molecule, a phospholipid, the lipid bilayer, DNA. So we're still at the molecular level. And now we are at a virus. Fitting material. That's another virus right there. It's HIV. Another virus, more viruses. So the largest virus is 0.00001 meters. So very, very small. Here is a single cell. This is a bacterial cell, very, very small, but still a single cell. There's a mitochondria. Mitochondria are actually larger than E. coli. Now we're at human cells. A white blood cell, red blood cell are about the size of a mist droplet. Skin cell. The human egg is the largest cell type. Those with really good eyesight can actually see it. It looks like a period typed on a paper in size 8 font. Dust mite, paramecium, amoeba. So amoeba are very large single-celled organisms. They're protists. So now I'm going to zoom out a little bit. So this is the largest cell, an amoeba, let's say that. Now I'm going to start zooming out a lot quicker, just to show you how small cells are. All right, you get the idea. I'll go till the sun. How about that? Did I pass it already? Maybe I passed it already. Oh well, it's still cool. Okay. Anyway, so that's just a cool way to show you just how small cells are. But the main idea is that cells divide in order to stay small. So why do cells have to be so small? You might remember that particles such as water and nutrients need to be able to diffuse into the cell, and waste needs to be able to diffuse out of the cell. Remember, diffusion is when particles move from high to low. The larger the cell gets, the harder it is to get particles into and out of the cell by diffusion. So the larger a cell gets, the harder it is for a cell to carry out diffusion. So I have a visual to demonstrate this. So let's say the blue particles are waste and the red particles are food. The food needs to be able to get into the cell, right? Move from high concentration to low concentration. The waste particles need to be able to get out of the cell, move from high to low. If the cell is large, then it has to travel from here all the way out to here. Same thing with this red cell, right? Or red particle. It's got to move all the way from out here to in here. If the cell is small, the blue particle only needs to travel this distance to get out, and the red particle only needs to travel this distance to get in. Okay? So the smaller a cell is, the easier it is to carry out diffusion. The larger a cell is, the harder it is to carry out diffusion. So it is beneficial for cells to be small. But over time, cells get larger and larger, right? They grow in G1 phase. They're filling up with organelles, with food, with waste, with all sorts of things. And if those particles cannot diffuse in and out because the cell is too big, it's grown too much over a certain amount of time, then signals will tell the cell to divide. It'll start the cell cycle, basically. It'll exit G0 or G1 and it will be given the signal to start the division process, to move into S phase and copy the DNA, and then go into G2, then go into M phase, okay? So it is when the cell grows to be too big where it can't do diffusion anymore, it will divide. So here's a more, you know, artistic representation, right? This is one big cell. Here's the nucleus. Here are many smaller cells. A particle would need to leave the nucleus and travel this entire distance in order to leave. In this smaller cell, a particle would only need to travel this distance to leave the cell, okay? So it is beneficial for cells to be small. So a cell size can be calculated using its surface area to volume ratio. We're going to bring a little bit of geometry into class today. So it's important to know how to calculate a cell size because you want to know how efficient it will be at diffusing, okay? So the way you calculate a cell size is by its surface area to volume ratio. So surface area is, the area, length times width of all of the sides. Well, volume is how much this geometric shape can hold. So first you calculate surface area. Here's a formula for surface area. It's measuring the area of each side of the box and then adding the numbers. So you want the area of this side, and this side. And then since there are two of each of those sides, right? There's this side and then the same thing over here, this side and then the same thing in the back, and then the one on the top and the one on the bottom. So it's 2 times A times B, right? Because that A times B is the area of this rectangle right here. But then you also need the same from the one back here. That is the surface area. You want this, how much space, is available on all of the surfaces of this box. So you do the area of this rectangle, the area of this rectangle, and the area of this rectangle, and then find, multiply each one by 2 because there's 2 of each sides, and then add it all up. So 2 times 4 times 5 gives you the area of this one and then the one in the back. 2 times 5 times 2, I'm using these numbers over here, gives you the area of B and C. So the one on the bottom and the one on the top. And then 2 times 4 times 2 gives you the total area of this one, the one on the left, and the one on the right. And then if you add it all up, you get 76 millimeters squared. Remember, if it's area, it's a squared number, okay? Then we need to find the volume. Volume is much easier. It's just length times width times height. So it's 4 times 5 times 2, which gives you 40 millimeters cubed. Then, you need to find the surface area to volume ratio. So ratio just means that you take the fraction. So at the bottom there, I'm showing that I'm doing surface area to volume, surface area over volume. First, I simplified the number. So it's not a nice clean fraction. Sometimes it simplifies where you can say like 3 to 1, 2 to 1. That sounds like a ratio where you put the colon in the middle. But this one didn't simplify nicely, so I just kept, the numerator over the denominator, and then I actually did the division. I did 19 divided by 10, and you get 1.9. Okay? So that would be the surface area to volume ratio. So now what I want you to do is go find any box around your house. It could be a tissue box, a box of pasta, an Amazon box, any box, whether it's big, small, whatever it is, even a jewelry box. Go find a box and use something you have to take the measurement, whether that's a ruler, maybe a tape measure. If you have like a toolbox, you can go try to find a tape measure. If you have like a sewing kit, there might be a tape measure, that you can use. So try to find a box and then take each measurement, the length, the width, and the height, and calculate the surface area to volume ratio of that box using the same formulas that I just showed you on the previous page. All right? So once you do that, we're now going to move into a lab for the day. So this is one of the really fun labs of the year, and it's sad that we're missing this one. But I wanted to still show it to you because it really does communicate this whole situation of why cells have to be small. So again, this is just a summary that let's say you have a really, really small cell that's 1 millimeter by 1 millimeter by 1 millimeter. Actually, that's a really big cell. Usually cells are measured in nanometers, which is 9 times smaller than a meter. So millimeter cells would actually be gigantic. But this is just for, for mathematical sake. So let's say you have a small cell and then a bigger cell. The surface area of a cube, this is a cube because all the sides are equal. The surface area is a little bit easier to calculate. It's 6 millimeters squared. Well, the volume would just be 1 times 1 times 1, which is 1 millimeter cubed. So the surface area here is pretty simple. It's just 6 to 1. This one would be 2 millimeters by 2 millimeters by 2 millimeters. The surface area is 24, while the volume is 8. And you can simplify that to 3 to 1. This one, the largest cube, has a surface area of 96 millimeters squared, a volume of 64 millimeters cubed. You can calculate this the same way you did on the previous 2 slides, and the ratio is 1.5 to 1. So you'll notice that the smallest cell has the largest surface area to volume ratio. So smaller cells have a larger and actually better surface area to volume ratio. So you want the cell to be small, and that means it will have a larger surface area to volume ratio. This means that the surface area is larger than the volume, okay? In this large cell, the volume is much closer in size to the surface area, right? There's not a great difference between the surface area and the volume. In a small cell, there is a much greater difference. The surface area is much higher than the volume, okay? So it's actually better for a cell to have a larger surface area to volume ratio because that means it's small. So it's kind of, what's the word I'm looking for? It's an inverse relationship. As the cell gets bigger, the surface area to volume ratio gets smaller. There's a smaller difference between the surface area and volume. So that means that if a cell's surface area to volume ratio gets too small, meaning the cell gets too big, the fusion cannot happen quickly enough and the cell will be forced to divide. Okay? So here's the lab setup. We use something called agar. Agar is kind of like a gelatin. It comes from seaweed. It's just very sturdy. It's a very rigid, dense gelatin. And in the lab, you prepare this agar to contain a chemical called phenolphthalein. Phenolphthalein is an indicator for changes in pH. It turns pink in the presence of a base. If remember we used cabbage juice as an indicator. It turns color when the pH changes. Phenolphthalein turns pink, like a fuchsia color, in the presence of a base. And you cut up this agar into 3 different cubes. A 3 centimeter cube where all the sides are 3 centimeters, a 2 centimeter cube, and a 1 centimeter cube. This is a really fun lab because you get to, chop up into, sorry, it's my phone ringing. You have a 3 centimeter, I already went over this. So it's really fun to cut up the agar. It's a shame we didn't get to do this. And then you also have a beaker of a very strong base called sodium hydroxide. So the idea is when you plop these 3 cubes into the agar, I'm sorry, I'm losing my mind. When you plop these 3 agar cubes into the sodium hydroxide, it'll turn pink, right? Because this is a strong base and you've put phenolphthalein into the cubes. And what will happen as the cubes sit in the sodium hydroxide, the sodium hydroxide diffuses into the cubes, okay? And as the sodium hydroxide diffuses into the cubes, portions of the cube turn pink. So you're actually able to see how much diffusion has occurred in the cubes. Okay, so I found this video of students doing the lab. This is not a video, of my personal students. It's from some class somewhere in the world, but it's funny. It's very much like your typical lab. I think the girls ask, wait, what are we supposed to do? Like every 2 minutes. But they recorded themselves doing the lab. I figured since we can't really do the lab, you can actually still get this kind of like point of view video as if you were doing the lab. So what they've done is they've cut up their cubes and then they're going to plop it into the sodium hydroxide and they let it sit for about 10 minutes. I'm not going to show you the whole 10 minutes because it's pretty boring. They just let the camera sit there and record. And then they take the cubes out and cut them in half to see how much of the cube has turned pink. The pink portion of the cube tells you how much diffusion occurred. So I'll start the video and I will skip around a little bit, but
3 centimeter cube, a 2 centimeter cube.
So they have their 3, their 2, their 1. I think they're going to get sodium hydroxide. There we go. Okay. Beaker of sodium hydroxide. And they put the 3 cubes into the sodium hydroxide, and you note the color change. You can see the cubes turning pink.
Let them sit for 10 minutes.
So they let them sit for 10 minutes. I'm going to fast forward a little bit. So they're just sitting there. They stir it a couple times. And then, oh, okay, then they start taking them out. So you can see even the solution has started to turn pink. I'm just going to pause for a second. Why has the solution turned pink? The reason the solution has turned pink is because some of the phenolphthalein that was in the cubes has also diffused out of the cubes and into the solution of sodium hydroxide. So while the sodium hydroxide is diffusing into the cubes and turning the cubes pink, the phenolphthalein that's in the cubes is diffusing out and into the sodium hydroxide, turning that pink. So you can see, just like a normal cell, food and nutrients are diffusing in while waste is diffusing out. In this case, the sodium hydroxide is diffusing in and the phenolphthalein is diffusing out. So now they're going to take them out.
Okay, now we have to take the cubes out and pat them dry.
Oh, I see on her shirt they're from Nebraska. Okay, then she spends like 5 minutes drying them off. Not even exaggerating. Still drying, still drying. Okay, then she finally goes in. And what they're going to do is they're going to cut them in half. They're going to open them up to see how much diffusion has occurred.
Where's my mortar and pestle? You tell her what to do. I'm gonna go to Rio.
So you can see on that middle one, there's still some white, as well as that one all the way to the left. The sodium hydroxide did not diffuse all the way into those cubes. But the smallest cube, there's really no white area left. So then what she's going to do, she's going to measure the depth of diffusion. She's going to take a ruler and measure that pink portion. That pink portion is the space that has turned pink from the sodium hydroxide. The chemical reaction between the phenolphthalein and sodium hydroxide occurred there. So that means that sodium hydroxide reached that far. So she's going to take a ruler and measure how far diffusion traveled, diffusion brought the sodium hydroxide into the cube. Okay, so this first one, she gets
It went in
half a centimeter, so 0.5 centimeters. The second one, she gets
in 4/10 of a centimeter.
She says 4/10 of a centimeter, which is close to 0.5. And then this last one, it has diffused all the way through. There's no white space left. And what she says is that it's diffused 0.5 centimeters. Now think about this. The cell was 1 centimeter by 1 centimeter, 1 centimeter by 1 centimeter by 1 centimeter. So by diffusing 0.5 centimeters, the sodium hydroxide actually went all the way through because it diffused 0.5 centimeters from all sides. So it came in 0.5 centimeters on one side and then 0.5 centimeters on the other side and met in the middle. So this is one part of the lab students actually usually get caught up on. They usually get that question wrong. They say that the sodium hydroxide diffused 1 centimeter. It did not. It diffused 0.5 centimeters still, right? The rate of diffusion does not change. So in 10 minutes, sodium hydroxide diffuses 0.5 centimeters into the agar. It just so happens that by diffusing 0.5 centimeters through the agar in a 1 centimeter cube, it goes all the way through, right? Because it diffuses 0.5 centimeters on all sides and meets in the middle. So then she holds them up and you can see 0.5 centimeters.
Okay. That's all. Is that all I need to record?
I think she's done. Okay. So you get the idea. It is a fun lab. And then usually if we were in class, I'd let you basically, chop it up into little itty bitty pieces and film like the ASMR videos. But so here's your results, right? This is called the depth of diffusion. How far did that sodium hydroxide travel into the cube? In all instances, it travels the same distance. The rate of diffusion is that sodium hydroxide diffuses 0.5 centimeters in 10 minutes. And all the cubes were in there for 10 minutes. So only 0.5, the sodium hydroxide can only travel 0.5 centimeters. But in this smallest cube, it only needs to travel 0.5 centimeters to reach the middle. In this large cube, traveling 0.5 centimeters does nothing, right? It doesn't even get to the bulk of the cell. So you can do a bunch of calculations to see how efficient the different sized cells are at diffusing, okay? So the 1 centimeter cube, you can calculate the surface area, the volume, the surface area to volume ratio. The depth of diffusion is the same for all of them, and the rate of diffusion, right, it's 0.5 centimeters in 10 minutes, so that means it's 0.05 centimeters per minute. And that never changes, right? But in the smallest cell, that's all you need. You only need 10 minutes for the food particles and the nutrients or whatever it is to get into the cell. In the large cell, 0.5 centimeters in 10 minutes gets you nothing, right? You need a much longer period of time for food particles and nutrients to get into the cell. So then you can actually calculate the percent diffusion. in the 1 centimeter cube, there was nothing left unpenetrated. The entire cell was pink, right? All 1 centimeter, the entire volume of the cell was pink. So we say it's 100% diffusion. In the 2 centimeter cube, there was 7 centimeters cubed. A volume of 7 centimeters cube was left white. So that means there was only 87% diffusion. Or I'm sorry, I went the wrong way. 7 centimeters cubed was pink. There was 1 centimeter cubed worth of, the volume of that cell that was still white. I'm sorry, I switched those. So there was 87% diffusion. In the 3 centimeters cubed, there was 8 centimeters left white and 19 centimeters cubed was pink. So although it seems like this is a lot, you didn't get to reach 8 centimeters cubed. 8 centimeters of volume was not penetrated. It didn't get any nutrients or food. So there was really only 70% diffusion. So the 1 centimeter cube is the most efficient in this case because there's 100% diffusion in the same amount of time. Okay, so this demonstrates why it is so beneficial for cells to be small. This is why cells have to divide if they get too big. They won't be able to do diffusion efficiently enough. All right, so that is our presentation for today. You saw why cells need to divide, right? Growth, repair, reproduction. And you saw when cells divide, when they get too big. And you got to see a glimpse into the Auger Cube lab. So please make sure your Edpuzzle is completed, and I will be checking that for completion. That is how you will receive attendance for today. All right, thanks so much for watching. Stay safe. Take care.